When an industrial facility is compromised by a cyber attack, the consequences aren't just digital. The result looks exactly like this, triggering immediate physical destruction. For decades, cybersecurity has focused on stopping data exfiltration and protecting digital privacy. But in an industrial context, the stakes are physical. This domain is known as operational technology, or OT. It consists of the specialized hardware and software used to monitor, manipulate, and control physical processes in the real world. This diagram outlines a minimal industrial control loop. Information flows from a sensor to a controller. Based on that data, the controller sends a command across the network to an actuator, executing a physical change, like opening a valve. Breaching this loop results in kinetic destruction and immediate threats to human safety. Scaling up from a single loop to an entire industrial facility, the network architecture becomes massively complex. The Purdue Enterprise Reference Architecture, or PERA, segments industrial networks into functional levels. At level 1, programmable logic controllers act as factory floor brains. Above them, in level 2, humans oversee processes through the operator and engineering workstations. Their privileges are strictly divided. The operator workstation is limited to monitoring and issuing basic commands. The engineering workstation holds root-level configuration authority, allowing engineers to write, upload, and alter the core logic programming of the PLCs. Because it translates human engineering intent directly into physical action, the engineering workstation sits at the apex of control within the industrial network. Industrial cybersecurity professionals identify these supervisory systems as their most vulnerable internal points. Over 56% rank operator assets as the components at greatest risk, followed by engineering assets at 50.5%. Incident data supports this assessment, with nearly a third of all control system attacks involving a compromise of the engineering workstation. A typical intrusion begins high above the factory floor. Attackers infiltrate the Level 4 enterprise IT network to establish a foothold. To move into the restricted OT network, attackers target the data historian. This database stores operational records and maintains authorized connections to both IT and OT environments. By compromising the data historian, adversaries abuse its trusted data channels to pivot from the corporate side into the restricted control network. Business integrations often pierce the theoretical air gap protecting industrial systems, creating a direct pathway for outside threats. Once inside the OT network, sophisticated adversaries employ a strategy known as living off the land. By targeting the engineering workstation, attackers gain the ability to destroy physical equipment using the system's own legitimate software. Engineering tools, such as PLC simulators used for testing code, frequently run with root debug privileges and lack proper sandboxing, allowing an intruder to bypass standard software restrictions. An attacker who accesses these tools can rewrite safety limits and alter logic parameters, weaponizing the control system against the facility it manages. However, resourceful adversaries can also bypass the network perimeter entirely by gaining physical access through transient cyber assets. 27% of OT attacks originate from removable media and transient devices, often introduced when an infected vendor laptop is connected to the network to perform maintenance. The greatest threat to an industrial facility is the weaponization of the exact tools designed to maintain it. When securing these environments, IT professionals often attempt to apply standard corporate endpoint security protocols directly to the engineering workstation. This creates a direct conflict between security priorities. While IT focuses on data confidentiality, OT requires continuous availability and physical safety. If a corporate antivirus agent mistakenly identifies an engineering process as malicious and quarantines it, the workstation may drop its connection to the PLCs, causing a loss of control that can lead to physical failure. Furthermore, industrial environments often rely on hardware with 20-year lifespans. These legacy systems frequently cannot be patched without halting the entire process. Blindly forcing IT security methodologies onto an OT environment introduces safety risks that often outweigh the theoretical security benefits. Defending an industrial control network requires zero-trust network access and strict logical segmentation. The engineering workstation must be isolated into its own secure zone, preventing lateral movement from the general IT network or other OT devices. Instead of relying on traditional antivirus, organizations must deploy OT-specific network security monitoring. Network security monitoring passively parses industrial protocols to flag anomalous behavior, such as a PLC configuration upload occurring outside of a scheduled maintenance window. The final layer of defense requires validating digital commands against real-world engineering workflows by cross-referencing electronic workstation logs with hard copy maintenance job cards. This allows security teams to verify that a logic change was authorized by a human engineer holding a physical permit to work. True defense of the engineering workstation requires abandoning IT assumptions to build a security culture centered on protecting the physical process.